Okay, so let's start with today's class. So in the previous class, we started discussing about something which is known as root locus. So root locus is nothing but the path that the closed loop, that the roots or the poles of the closed loop uh, system follows when the a certain parameter of the a certain system parameter is varied. Okay, so if you have an open loop system and you have a certain gain of that open loop system, which is, let's say, that is variable or adjustable. Now you make a closed loop system using that open loop system. Okay, so now, so the first thing that the moment you make a system closed loop, so the first thing that you need to understand is that by connecting a feedback, what is happening is that the poles and zero position uh, of the open loop system, that is being changed depending on how much feedback you have, whether you have a unity feedback or something else. Depending on the amount of feedback that you are providing, the position of the poles and zeros of the closed loop system will be different from that of the open loop system. Okay, so and obviously depending on where the pole of this closed loop system is lying, that will govern whether your closed loop system will be a stable system or not. If the poles they are lying on the right half of the S plane, then your closed loop system will be unstable. So what we need to do is that we have to find out what is the, or we have to find out information about the stability of the closed loop system, depending on the position of the closed loop poles. Okay, so root locus is basically one of the methods of doing this, wherein where what you can do is that just from the information that you have on the poles and zeros of the open loop transfer function, from that information you can find out what will be the position or how the roots of the closed loop system, those will be changing if you are varying a certain parameter. Let's say gain, in most of the cases gain of the system is usually changed. So depending on how you are changing the gain, and on based on that, how the position of the poles of the closed loop system is changing. That is basically the main concept of root locus. Okay, so we saw in yesterday's class that there are certain basic conditions of root locus. So the conditions which need to be satisfied for so condition. So there are two conditions. One is the magnitude condition, which is given by this. That is the magnitude of G1s H1s will be equals to 1 by k, where G1s H1s is the transfer function which does not contain any term, does not contain the variable term. So k is the variable. So here we are changing, k is variable. So we are changing k and we are observing the position of the roots of the closed loop system. Okay, so the magnitude condition is given by G1s H1s equals to 1 by magnitude of k for k when k is varying from minus infinity to plus infinity. And the angle condition is that the angle of G1s H1s should be equals to 2q plus 1 into pi when we are varying k from 0 to plus infinity, and this angle condition should be equals to 2q pi when the value of k is being varied from minus infinity to 0. Okay, so in practice, whenever you are constructing a root locus, we try to find out all the points that are present in the S plane that satisfies the angle criteria. So these are the two angle criteria. So if the point S in let's say you take a random point on the S plane and you apply these two angle criteria. Okay, so if that point is satisfying this angle criteria, then we say that that corresponding point is a point on the root locus, and you can find out the value of the gain at that position from this magnitude criteria. Okay, so basically what we do here is that this we have already talked about yesterday. Just to recap, so if you have a point S1 and you already know the pole 0 configuration of the open loop system. So what you do is that you draw different vectors starting from the corresponding poles and zeros to the point that we have selected. Okay, so once you have drawn the vectors, what you can do is that you can find out what are the angles that these vectors are making with the real axis. Okay, so that those angles, so from that once you know these angles, so you can simply apply this this angle criteria, and you can see that if the angles that these vectors from zeros to this point, that is making addition of that minus the angles which this the vectors from the poles to this point, the difference of these two things, if that is equals to, that is an odd multiple of 180 degree for obviously k ranging from 0 to infinity, then you say that this point S1 is lying on the root locus, Okay, so and similarly you can find the gain at that point S1 just by taking the from this main equation. So you just take S1 magnitude of S1 plus Z1 divided by magnitude of S1 into magnitude of S1 plus P2, S1 plus P3. From here you can find what will be the value of the gain at that point that we have selected. So ideally what you need to do is that you have to find out all the positions or all the points on the S-plane which satisfies this angle criteria, and if you connect that all those points you will get the root locus. But obviously you cannot so if you have to find out all the points individually, that will become a very tedious process. Okay, so for that what we do is that we have certain rules which you follow. If you follow those rules, then it becomes much more easier to construct a root locus. Okay, so the step 1 is find all the points in the S-plane that satisfies the angle criteria for both k greater than equals to 0 or k less than equals to 0. And step 2 is that you find the value of k at the points on the root loci or the complementary root loci, whatever you have, from the either you can find it from the angle criteria or you can find it simply from the root locus graph that you have plotted. From that graph itself you can find out the value of gain at a certain point. Okay, so now let's see what are the rules for construction of this root locus. Okay, so the first step is like you have to, we have since, so now we'll mostly focus on the variation of k from the range of for positive case. Okay, so we will see if we are changing the value of k from 0 to, so if k is being changed from 0 to infinity, for this range what will be the corresponding root locus that we get. And if you know that that corresponding root locus, then it becomes easier to draw the complementary root locus because they are actually symmetrical to each other. Okay, so the first step is to find out what are the points, that is k equals to 0 points. Okay, so k equals to 0 means they are the poles of the open loop transfer function, that is GSHS, and we say that this k equals to 0 point, they are the starting point of the root locus. Okay, so now let's say that you have a characteristic equation which is given by this s into s plus 2 s plus 3 plus k into s plus 1 equals to 0. So from here you can write that the open loop transfer function will be equals to k s plus 1 divided by s plus 2 s plus 3. Okay, so this is your open loop transfer function. So from here you see that if you apply in this characteristic equation, if you put k equals to 0, then this equation translates into s plus 2 into s plus 3 equals to 0. So the values of s becomes s equals to 0, minus 2 and minus 3. Right? So and s equals to 0, minus 2 and minus 3 are nothing but the poles of this open loop system, which is given from this. So you can say that k equals to 0 points correspond to the poles of the open loop transfer function, and they are the starting point of the root locus. The root locus will always start from the poles of the open loop transfer function. Okay, then next we have to find out what are the k equals to, let's say, plus minus infinity, or in this case since we are dealing with k ranging from 0 to infinity, so let's say the k equals to infinity points. Okay, so k equal to infinity points will be, so similarly in this equation, if you put the value for very large values of k, you can approximate this equation as k into s plus 1 equals to 0. So for that case, you can see that it is, so the root of this equation is the s equals to minus 1, and s equals to minus 1 is nothing but the 0 of the open loop transfer function. right? So you can say that for k equals to infinity, that the k equals to infinity point, that indicates the zeros of the open loop transfer function, zeros of GSHs, and the zeros of GSHs, they are the ending point of the root locus. So a root locus, it starts from the pole of the open loop transfer function and it ends at the zero of the open loop transfer function. Okay, so in this case, let's say that you have, if you draw the pole and zero in the S-plane, if you draw the poles and zeros, so you have only one zero over here and you have three poles. So you will be having, so there will be root locus will be generating or will be starting from this pole, and this pole, and it will be ending at this zero. We will see how the root locus are, how the paths, the root locus path is being followed by in the subsequent steps. Okay, so then, so the first step is to find out what is the k equals to 0 point, which is equals to the which is nothing but the poles of the open loop transfer function. K equals to infinity point, that is the zero of the open loop transfer function. Then we want to find out what is the number of separate root locus which are present. So as we already know that root locus is the locus that one root takes when k is varied from 0 to infinity. Since we are talking about only about root locus, we are not talking about the complementary root locus. So that means that the value of k is ranging from 0 to infinity. So the number of separate root locus which are present in the overall or the number of branches in the root locus, that is equal to the number of roots of the equation, or you can say that it is equal to the number of finite open loop poles which is given by n, or the number of finite open loop zeros, whichever is the greater. So if n is the number of separate root locus which is present, so let's say n is the number of separate root locus which is present. So the value of n will be equals to p if p is greater than z, where p is the number of poles and z is the number of zeros, or it will be equals to 0 if the value of p is less than value of z. So depending on whether the number of poles is more or the number of zeros is more, depending on that, the maximum of these two will be equal to the number of separate root locus. Sorry. So for the characteristic equation that we were talking about, so here you see that we have three poles, so n equals to 3, and we have 1 0, so m equals to 1. So this is basically a third order equation. Third order equation means that it has three roots of the equation are present. That means that the number of root loci which will be there is equals to 3. Okay, then the fourth point is that the symmetry of the root loci. The symmetry of the root loci means that this is a property of the root locus. You can say that the root locus is always symmetrical with respect to the real axis of the S-plane. So if you can draw the root locus in one, in let's say the positive part. So if you have, if this is your, so this is your imaginary axis, this is your j omega axis, this is your sigma axis. So if you know the plot or the root locus in the top half of this real axis, then you can simply take a mirror image of that, and that mirror image will give you the overall root locus. Okay, so let's say that you have so one pole over here. One pole over here. Okay, so and let's say that you don't have any zeros, or yeah, let's say you don't have any zeros. So if you see that if you draw the root locus of this plot, so it will be something like this, and it will go like this. Okay, so you see that this root locus, so that means it starts at the poles. So both the root locus will start from the pole, and if you observe the overall root locus, you will see that this is actually symmetrical to the real axis. So if you know the root locus in the positive part of this, or the upper half of this real axis, you can simply draw the root locus in the bottom half, or the bottom half of the real axis. Okay, so this root locus is always symmetrical with respect to the real axis of the S-plane. Now, what if you have in your system, you have the number of poles and the number of zeros. So if the number of poles and zeros are equal, then all the root locus branches, they start at a finite open loop pole and they will end at a finite open loop zero. So let's say that if n, so if you have n number of poles, n number of poles and m number of zeros, we know that poles are the starting point and zeros are the ending point of the root locus. Okay, now since n equals to m, so that means you can say that all the root locus, they will start at finite open loop poles and they will end at finite open loop zeros. Okay, but now let's say that if the number of poles in your system, in the open loop system, that is more than the number of zeros. Okay, then what will happen if the value of n is greater than m? So that means there will be, so there are m finite zeros. Okay, so there will be m number of root locus branches which will start at finite open loop poles and end at finite open loop zeros. Now you have something extra, some n minus m finite poles, finite open loop poles which are there, which do not have a corresponding finite zero where the root locus can end. Okay, so what will those root locus do? So those root locus, what they will do is that they will start at a finite open loop pole and they will end at infinite open loop zeros. So if you have n greater than m, so that means number of poles is more than number of zeros, then m number of root locus branches, they start at finite open loop poles and end at finite open loop zeros, and the rest, that is n minus m number of root locus branches, they start at finite open loop poles and end at infinite open loop zeros. Similarly, if the number of zeros is more than the number of poles, so that means then what we will have is that n number of root locus branches, they will start at finite poles and end at finite zeros, and the difference, which is m minus n number of root locus will start at infinite pole open loop pole and end at finite open loop zeros. Okay, and the moment we are talking about either the root locus is ending at an infinite zero or starting at an infinite pole, that means that the value of n is not equal to m. So that means the root locus is either approaching infinity or it is coming from infinity. So they, like how these root locus are approaching to the infinity or coming from infinity, they are given by these asymptotes. You can say that asymptotes give the direction of these root locus branches. So we'll find out how these asymptotes look like. So the moment you have, if you have more number of the number of poles and zeros are not same, then you will have to, these asymptotes will give you the direction of those root locus branches. Okay, so now we'll find out what are the asymptotes of the root locus. So asymptote means the behavior of the root locus when s is tending to infinity. Okay, so you can say that for large values of s, the root locus for k greater than equals to 0, they are asymptotic to straight lines, or they are asymptotes with angles theta q, where theta q is given by 2q plus 1 into pi divided by n minus m, and the value of q, it takes values from 0, 1, 2 till n minus m minus 1, magnitude of n minus m minus 1. So this will be the angle of the asymptotes which are present if the number of poles and number of zeros in the open loop system, they are not equal. Okay, this is for k greater than equals to 0. Similarly, if you want to find out the asymptotes for the complementary root loci, that is k less than equals to 0, then the asymptote angle will be given by theta q is equals to 2q pi divided by n minus m, and the value of q will still remain the same. It will start from 0, 1, 2 and it will go till modulus of n minus m minus 1. Okay, so we have found out what will be the asymptotes of the root locus look like, or where the this s when s is tending to infinity, what will be the behavior of the root loci. Next, what we can find out is that what will be the intersection point of these asymptotes. Okay, So now the intersection of n minus m asymptotes of the root loci, or you can say twice of n minus m asymptotes of the complete root loci, because complete root loci comprises of root loci plus the complementary root loci. So there will be n minus m asymptotes in root loci and similarly n minus m asymptotes in the complementary root loci. So overall there will be 2 n minus m asymptotes in the complete root loci. So this intersection of n minus m asymptotes of the root loci, they lie on the real axis of the S-plane, and the intersection point is given by this formula. So this formula and this intersection point of the asymptotes, this is known as the centroid, and centroid is given by summation of the real part of the poles of GSHS or the open loop transfer function minus summation of the real part of the zeros of the open loop transfer function divided by the difference between the number of finite poles minus the number of finite zeros. Okay. Now let's see an example, then things will be more clear. So let's say you have been given with a characteristic equation which looks like this. So from here you can write that the open loop transfer function GSHS is equals to k into s plus 1 divided by s plus 4 into s square plus 2s plus 2. Okay, so the first step to constructing this root loci is, first of all, we'll find the k equals to 0 points, which are nothing but the poles of GSHS. So the poles are 0. So from here you get pole 0, you get minus 4, and if you factorize this term, then you will get that there is a pair of complex conjugate pole which lie at minus 1 plus minus j1. Okay, so these are the k equals to 0 point or the starting point of the root locus. Okay, then we will find out what are the k equals to infinity points, which are nothing but the zeros of GSHS. So 0 of GSHS is at s equals to minus 1. Okay, now since this is a fourth order characteristic equation, so that means there will be 4 root loci will be present. Okay, and here you see that the number of poles n is equals to 4, while the number of zeros m is equals to 1. So you can say that n is not equal to m. So n is not equal to m. So that means that, and in fact the value of n is greater than m. So you can say that m number of root loci will start at finite poles and end at finite zeros, and the n minus m, that means 3 root loci will start at finite poles but they will end at infinite zeros. And the asymptote angles you can find by for this root loci. So the asymptote angles will be theta 0. You can find, so this from the previous equation, from here you can find theta 0 will be equals to pi by n minus m being 3. So you have pi by 3, which is 60 degree. Then you have theta 1, which will be equals to 3 times of this theta 0, which is 180 degree, and you will have theta 2, which will be equals to 300 degree. Similarly, if you want to find out for the complementary root loci, you will just have to use the other other criteria, and from there you can find out what will be the angle of the asymptotes. Okay, so if you draw the in the S plane, so you have omega and j omega and theta and sigma over here. So you have one pole at 0, so another pole at minus 4, and there will be some other. So one pole is here. So this is one pole that you have. So this is another pole. There is one complex pole over here, another complex pole over here. So you have 4 poles and you have 1 0. That 0 is lying over here. Okay. So what you can do is that, so you can draw, so the asymptote angles will be at 60 degree, 180 degree and 300 degree. So there you can draw one asymptote at 60 degree, which is this one. Another asymptote at 180 degree, which will be this one, and the other asymptote at 300 degree, which will be this one. So, and these dotted lines are basically the asymptotes of the complementary root loci, and the solid lines, they are the asymptotes of the root loci. And the point of intersection, which is this, which is known as sigma, that can be found out from this previous equation, that is the real summation of real part of the poles of GSHS minus real part of the zeros. So you can write that Sigma 1 is equals to summation of the real parts of, so the real part of the poles is 0 plus 4, 0 plus of minus 4 plus of minus 1 plus of minus 1 minus real part of the 0, which is minus of minus 1, divided by n minus m. N minus m is nothing but 3. So from here, so this is equals to, this gets cancelled out, so this is minus 5 by 3. So you can find out what is the intersection or the centroid intersection of this asymptotes of the root loci. Okay. Next, now similarly for let's say for a different open loop transfer function, if you have k by s into s plus p1, let's say. So here you have only 2 poles and you don't have any zeros. So that means the value of n is equals to 2, the value of m is equals to 0. So n minus m is equals to 2. So there will be 2 complete root loci, and you can find out what will be the angles. So theta 0 will be equals to 90 degree and theta 1 will be equals to 270 degree for k greater than equals to 0. And similarly, you can find out for the complementary root loci also. And the centroid will lie at a position minus p1 by 2. Here you see that the two this asymptotes, they are at one is at 90 degree, another one is at 270 degree. In the previous case, depending on where the poles and zeros or how many poles and zeros are present in your system, accordingly your asymptote angles and the centroid, those things will change. So now so in the previous system we had only s and s plus p1. Now let's say that we add 2 more poles to the same system. So now we have 4 poles. So you have n equals to 4, m is still equals to 0. Okay, so the moment you have 4 poles in your system, you see that the asymptote angles obviously will change, right? So now the asymptote, in the previous case, the asymptotes were, there were 2 asymptotes and the angles were 90 degree and minus 270 degree. And now here we have 4 asymptotes and the angles will be 45, 135, 225 and 315. So these angles you can find out from that from the criteria. So that the criteria that we had was that theta q will be equals to 2q plus 1 into pi by n minus m. This is for k greater than equals to 0. And for this one we had theta q is equals to 2q pi by n minus m. This is for k less than equals to 0. And the centroid also you can find out. So here you see that you have 4 asymptotes of the root loci. So one is at an angle of 45 degree, which is this one. Another one at an angle of 135 degree, which is this one. Then you have at an angle of 225 degree this one, and the other one is that this one at an angle of 315 degree. So you have 4 asymptotes at the angles which you can find out from this equation. So till now we have found out the asymptotes, the centroid where the asymptotes will intersect those points. Okay. So next we need to find out that whether a root loci is present on the real axis or not. Okay. So there is a criteria or a condition which needs to be satisfied if a root locus is or a root loci is present on the real axis of the S plane. Okay. So for a root loci, on a given section of the real axis, a root loci for k greater than equals to 0 can be found if and only if the total number of real poles and zeros on the right side of that section is odd. Okay. Let's take an example. So here, let's say we have one pole over here. There is another pole over here. There is a 0 here, another 0 here. We have 2 complex conjugate poles. And there is, so this is the position of the poles and the zeros. Okay, so now the root locus for this k greater than equals to 0, for this k greater than equals to 0, a root locus will be present on the real axis if the summation of the number of real poles and zeros on the right side of that section is odd. Okay, so while we are considering the presence of root locus or the existence of root locus on the real axis, this presence of complex poles and zeros, they do not affect the existence property of the root locus on the real axis. So we are only concerned about the real poles and zeros which are present on the real axis. Okay, so here you see that if this part of the, let's start from this part. So if this part is a part or is a portion of the root loci, so that means the number of poles or the summation of the number of poles and zeros on the right hand side should be equals to is the odd. So if you consider this zero, so to the right side of it, so you have 1, 2, 3. So you have odd number of poles and zeros on the right side of this section. So that means this section will lie on the okay, no. So there is another pole over here. Okay, yeah. So if you consider this section, let's forget about this. If you consider this section from here till here you see for this section you have 1, 2, 3, 4, 5. You have 5 number of odd number of poles and zeros. So that means root locus will lie in this section. But for this section, you see that for this part from here till here, for this part the number of roots, the total number of poles and zeros to the right is 1, 2, 3 and 4. Which is an even number, so that means there won't be any root locus between this point and this point. Similarly, you check between here. So in this region, so from here to here, in this region you have 1, 2, 3. So you have 3 poles and zeros on the right hand side. So that means that this portion is a part of the root locus. Similarly, this portion will not be a part of the root locus because you have odd even number of poles and zeros, and again this portion will be a part of the root locus since it has odd number of poles and zeros on the right hand side of it. Okay, so depending on the total number of real poles and zeros present on the right hand side of that corresponding section, if that is odd, then we'll say that that section of the real axis, that is a part of the root locus. And for a complementary root locus, the criteria is just the opposite. So for a given section on the real axis, it is a part of the complementary root locus if the total number of real poles and zeros on the right side of that section is even. Okay, and if you see that, if you just observe these two criteria, you can say that the complementary root loci will be found in the sections of the real axis which are not occupied by the root loci. Hence the name also suggests like that complementary means wherever the root loci is present on the real axis or wherever the root loci is not present on the real axis, you will find the complementary root loci over there. And also this complex poles and zeros, they do not affect the existence property of the root loci on the real axis. Okay, so next what we need to find out is that, next we need to find out the angle of departure from poles or angle of arrival at the zeros. So why angle of departure? Because all the root locus, they start from poles. So that means so we have to calculate what will be the angle of departure from let's say a complex pole. Okay, and if you have a complex zero, then we have to find out what is the angle of arrival of the root locus to that zero. So basically this angle of departure or the angle of arrival, it denotes the behavior of the root locus near that corresponding pole or zero. Now the angle of departure basically of a root locus for k greater than 0 from poles or arrival at zeros, they can be found by assuming a point S1 on the root locus which is associated with that corresponding pole and which is lying very close to the pole that we are interested in. Okay, so what we will do is that we'll select a point S1 which is very close to the pole or the zero from where whose angle of departure or angle of arrival we want to find out, and then we apply these following equations. So these equations are basically, so again we'll apply this equation, angle of G1 H1 S should be equal to summation of the angles drawn from the zeros to this point S1 minus summation of the angles drawn from the poles to the point S1. If that condition, if that this difference is equals to 2q plus 1 into pi for q will take 0, 1 and 2. Then this is for k greater than equals to 0. Then from here we can find out what will be the corresponding angle of departure from the pole. Or similarly, if you have k less than equals to 0, the criteria that we need to or the equation that we need to use is that the equals to term will be equals to 2q into pi. Okay. So now let's see how to find out this angle of departure. Okay, so let us say that you have this is the open loop transfer function which is given. So we'll start from the basics. Okay, so first we'll find out the number of poles. So you have 0, minus 3, minus 1, plus minus j. Okay, then you find out what are the asymptotes of the root loci. Done. Then the third step is find out what is the centroid. This is also done. Then in the fourth step you find out that which portion of the real axis they lie on the root locus. Here in this case you see you have one pole at 0, you have one pole at minus 3, another at here, another here, and we do not have any zeros. Okay, so for this portion you see that this portion will lie of this real axis. It has a single one pole on the right hand side of it. So that means that is an odd number. So you can say that this portion will be a part of the real of the root locus. But if you consider the portion from here till here, here you see that to the right side of it there are two poles. So that means we are actually not interested about the complex conjugate poles. So these do not come into the picture. So for this portion, this portion of the real axis to the right we have even number of poles. So that means this will not be a part of the root locus. So the root locus will be present on the real axis between these 2 points, between minus 3 and 0. Okay. So next what we need to find out is that what will be the angle of departure, and we have already drawn these asymptotes. So we already know these asymptote angles we have drawn. So these are the 4 asymptotes that we have and they are intersecting at, so this is the centroid. Sigma 1 is minus 5 by 4. Okay, and this part is on the this part of the real axis is a part of the root locus. Now if you want to find out the angle of departure from this angle of departure of the root locus from this complex pole, let's say this is minus 1 plus j. So what we do is that we take a point which is very close to this one but not equal to not the same point. So we take a point which is very close, which is let's say S1, and we find out what will be the corresponding angles that these vectors or these phasors will make if you draw these phasors. Okay, so you have like 4 phasors. So one is from this pole to here, another from this pole to here, this pole, and another from this pole. So we have 4 phasors. So let us say that the angles of these phasors are theta 1, theta 2, theta 3, and theta 4. Okay, and what we need to find out is that we have to find out what will be the value of this theta 2 from S1. Okay. So what we can do is that we can simply find out what are the values of this, because and now since we are considering this point S1 is very close to S, so you can say that this is almost equal to, for the sake of the calculation, you can take that the value of S1 is equals to the pole that we are interested in. Okay, so that means from here you can find out the angle between of this phasors. So this phasor angle will be equals to tan inverse of this real imaginary part by the real part. Okay, so similarly you can find out what will be the angles that these vectors are making with this point S1. Okay, so this theta 1 is equals to 135 degree, theta 3 this is equals to 90 degree, and then theta 4, let's say if this is theta 4, this is equals to 26.6 degree. And what we need to know is that what will be the angle of the from this S to S1. Okay, so the vector S1 or S minus S1, that vector is we are interested in the angle of that particular vector, which is given by theta 3. So if you just simply equate this equation, substitute the value of theta 1, theta 3 and theta 4, you will find that the value of theta 2 is equals to, it's coming as minus 431.6 degree, or you can just say that this is simply equals to minus 71.6 degree. So just add 360 degree to it and you will end up with this one. So that means that the root locus, which is starting from this complex pole, that will depart this pole at an angle of minus 71.6 degree. So this angle will be minus 71.6 degree, and after that it will follow this asymptote. Okay. Now how this root locus is present here, let's say, just to understand here, is like, suppose you have two poles over here and there is a root locus over here, right, in this real axis. So that means the root locus will start from this pole, it will move towards the right, okay, and similarly another root locus will start from this pole and move towards the left. Now the number of zeros in this, finite zeros in this system, is 0. Okay, so that means all the root locus, they will end at infinite zeros. Okay, so what will happen is that, so you can well understand that if these two root locus are moving towards each other, and if the terminal point of these root locus is infinity, so that means something should happen, like these two root locus should meet somewhere on the real axis, and from there they would sort of diverge or break and then move towards the infinite zero. Okay, so infinite zero, and it will follow the asymptote. So these are the asymptotes which were already there. So after meeting and then breaking, what they will do is that they will simply follow these asymptotes and go towards infinity. Okay, so this will be a part of the root locus, you can say. And for this complex pole that we have, so the root locus will start at an angle of minus 71.6 degree and then slowly move towards the infinite zero following this asymptote. So it will go something like this. And similarly for the other complex pole, since this is symmetrical with respect to the real axis, so the similar kind, or just a mirror image of this, will be the root locus from the other conjugate pole. Okay, so now you see that here the root locus, which is starting from this complex pole and going towards infinite, that is actually intersecting the imaginary axis. Okay, so the point at which this root locus is crossing or intersecting the imaginary axis, that is a point of interest to us. Okay, so this point of intersection of root locus with the imaginary axis, that can be found out, and the corresponding value of the gain, that can be found out from the Routh-Hurwitz criteria. Okay, so if the root locus is crossing or intersecting the imaginary axis, that means that, and in the Routh array, when we have studied the Routh-Hurwitz stability criteria, if you remember that if all elements of a row in the Routh array are 0, that means that there will be a pair of either repeated poles in the system. That means that if all the elements of any row in the Routh array are 0, that is the case, that is the condition when the root locus branch is actually intersecting the imaginary axis. Okay, so in order to find out what is the point of intersection and the corresponding value of k, we have to form the Routh array. We have to identify the row in such a way that if we make the first element as zeros, then the entire row becomes equals to 0. Okay, so since we have an unknown or a variable k, so we will have the first or some of the elements in the Routh array will be in terms of k. Okay, so we have to identify the row in the Routh array such that if we make the first row or the first element equals to 0, subsequently all the other elements in that entire row becomes equals to 0. For that corresponding value, and then we have to find out what is the value of k for this condition or for this combination. So once we know the value of k, so that means we can say that the point at which this root locus is actually intersecting the imaginary axis, at this point the value of k is found out from the Routh array. Okay, and for that corresponding point, when you substitute this value of k in the auxiliary equation, so the auxiliary equation is the equation that you are forming using the coefficients of the row which is prior or just before the row of all 0 elements. Okay, so that is the auxiliary equation. So if you substitute this value of k which you have found from here and that value in the auxiliary equation, you will find out that what will be the intersection point of the root locus with the imaginary axis. So that will give you the value of the s, and or rather you can say that will give you the value of omega, which is the point of intersection of the root locus with the imaginary axis. Okay, so now let's say that you have a transfer function or an open loop transfer function like this. So 1 plus GSHS will be equals to this. So you have this characteristic polynomial. So you can, from this characteristic polynomial, you can form the Routh table. Okay, so this is the Routh array that we have. So 1, so the odd terms 1, 8 and k will come in the first row, and then the even terms 5 and 6 will come in the second row. Okay, and then correspondingly you can find out what will be the you fill up the Routh array. Okay, so once you have filled up the Routh array, you see that for this corresponding row, that is s to the power 1, for this row, that if we make this term is equals to 0, then all the terms in this row are, or all the elements in this row becomes equals to 0. Okay, so that means that this, from this row we can find out what will be the value of k. So you equate this term will be equals to k, so k equals to 8.16. So that means this is the value of k at the point of intersection of the root locus with the imaginary axis. Okay, and in order to find out the value of that point, that you will get if you write the auxiliary equation, which is done from this equation. So you have 6.8 s square plus k equals to 0. Substitute this value of k 8.16 and you will find that the value of s is equals to plus minus 1.095 into j. So that means the value of omega is given by plus minus 1.095. Okay, so the moment you have plus minus 1.095, if you see this figure, so you see that there are like 2 points at which the roots are actually intersecting the or the root locus is actually intersecting the imaginary axis. One because of the root locus which is starting from this pole minus 1 plus j, and the other for the root locus which is starting from minus 1 and minus 1 minus j. So you can find out, so this value is plus 1.095 j and this value is minus 1.095 j, and the corresponding value of the gain is 8.16. From here, if you observe that the moment you cross this point, so that means this root locus is now going into the right half of the S-plane. Okay, so since the root locus is going to the right half of the S-plane, so that means that this is going into the instability region, because this right half of the S-plane is the instability region, and this is the stable. The left half is the stable region. So this is unstable region. Right. So now you can say that, so this is the limiting, or you can say that this is the limiting value of gain, beyond which if you increase the value of gain more than that, then your system will become, the closed loop system will become unstable. So from this root locus plot, you can find out what will be the range of k's for which the system the closed loop system will remain stable. Okay, so it's done. Now then comes the point, the concept of the break-in or the breakaway points. Okay, so basically this break-in or the breakaway point, that corresponds to a point in the S-plane where multiple roots of the characteristic equation occur. Okay, so when I was talking about this graph, you see that there are, so the root locus which are starting from these two poles, they are actually moving towards each other. So obviously they are moving towards each other means they will meet at some point. So once they meet, what they will do is that they have to go somewhere after meeting, right? So where will they go? So what they will do is that they will break away from that point. Obviously they can't go back to the previous position, because the poles, it started from the pole and it has to end at a 0. So that means after meeting, what they will do is that they will break away and they will move in opposite direction, and they will correspondingly either go to a 0. So that 0 can be a finite 0, that 0 can be an infinite 0. In this case, since we don't have any finite zeros in our system, so after breaking away, they will move towards the infinite zeros. Okay, following the asymptotes that we have already found out. Okay, so now what we need to do is that we have to find out what are these breakaway or the breaking points. So breakaway point comes when you have two, when the root locus is starting from two poles and it is moving towards each other. And breaking points means that the root locus, they have started from somewhere else, and there are, let's say you have two zeros on the real axis, and the root locus is actually coming on the breaking into the real axis, and from there they are moving towards the two zeros that you have. Okay. So basically this breakaway or breaking points on the root locus, they correspond to a point in the S-plane where multiple roots of the characteristic equation occurs. So multiple roots of the characteristic equation means in the closed loop system, you will have multiple repeated roots at that position. Okay. So now you can say that if two or more branches of the root locus, they meet at a breakaway point, then they depart in the opposite directions. Now, if there is a real axis, real axis root locus branch which is present between two open loop poles, then what will happen is that there will be a breakaway point in between those two open loop poles. If there exists a real axis root locus branch between two open loop zeros, then what will happen is that there will be a break-in point between the two open loop zeros, and after the breaking in happens, then the root locus will move towards the two zeros. Okay, so if you have, so let us say you have two poles over here. Okay, so if this part of the branch is a portion of the root locus, so then what will happen is that it will start from here. Let's say they will break somewhere here and then move outside. Okay, so then it will move towards infinity, and this is k equals to minus infinity. This is point k equals to 0. This is also k equals to 0. And similarly, if you have, suppose you have two zeros so two zeros means this is k equals to infinity, this is k equals to infinity. Okay, sorry. So that means what will happen is that, suppose let's say the root locus is coming from somewhere over here and from here somewhere over here. So that means these root locus, they are coming in, and this is the breaking point, and after breaking in, one part is going towards this finite 0 and the other part is going towards this finite 0. So you will have a breaking point between two zeros if there is a 0 or two zeros exist. If the branch of the root locus exists on the real axis between two open loop zeros, and you will have a breakaway point if a branch of the root locus exists on the real axis between two open loop poles. Okay, so now if there are n root locus approaching or departing from a breakaway point, either a breakaway point, if they are approaching, that means it's a breaking point. If they are departing, means it's a breakaway point. So if there are n root locus approaching or departing from a breakaway or a breaking point, then they must depart at an angle of 180 degree divided by n. Okay. Now we'll see that how we can find out what is the to calculate this break-in or the breakaway points. So I think we'll deal with that in tomorrow's class. So do you have any doubts till now? Like understanding the Routh-Hurwitz criteria, which we have talked about earlier, then this the basic principles or the steps that you need to follow while constructing this root locus. So do you have any doubts till now?
No, ma'am.
Okay, fine. Then the quiz I have already posted in the group that the quiz will be on next Tuesday, and the instructions are also will be similar to the first quiz only. So we'll have the quiz from 6 to 7, and by 7:15 you will all have to submit the responses as well as the rough work for the quiz. Okay.
Yes, ma'am.
Okay. So thank you, everyone. We'll again have our class tomorrow. Thanks.
Thank you, ma'am.